Okay, so here we have, we're still fall 2014 exam number 2 for strengths materials. And this is problem number 3. You have the PDF of this exam and the solutions to this exam. But again, try to work it out with looking at anything to make sure you can work it out. So we want to determine the displacement of point C on an axially loaded member. The members are square in cross section. So square. So when I look at this, some students will say, oh, the area is 10 inches squared. No, it's 10 inches, which means this is also 10 inches. This is also 20 inches. So look at your units. Member AB is made of aluminum. So this is aluminum. Member CB is made of steel. So I want to find how much, and I can clearly see both of these are providing compressive forces, so I can clearly see that C is going to go down to a C prime. And so the delta from C to C prime is going to be made of delta from B to C plus the delta from A to B, or B to A. I should be more consistent. C to B, B to A. Okay, so first thing I'm going to do is I'm going to do a free body diagram for statics or equilibrium, whatever you want to call, and I'm going to make my cut right here. So I have 5,500 kips going down, and visually I can see that the force in BC has to be 5,500 kips pushing back up, so we are in compression. Then I'm going to cut down here in the second part from A to B. And remember, you have to show everything above or everything below. So if I want to use the bottom piece, I have to find my reactions. Otherwise, everything above, everything below. So we have something that looks like this. And I'm just going to go ahead and make this a little bit bigger just so you can see where I've cut. And this is the force from B to A. So here is 5,500 kips. And then here is 6,000 kips. I can see they're both in compression, so I can visually let you know that this is pushing back up equal and opposite. And our internal then is 11,500 kips. And again, it's in compression, so we're going to be getting shorter. Okay. Now I need to figure out my displacements. As I push this down, I'm going to get that delta from B to C. As I push the whole thing down, I'm going to get a change in length here from A to B. And I need to find both of those so I can sum them up. And they should both be negative. So let's start with our A36 steel. Well, I know that stress equals E times strain. And I know that stress is that internal force divided by that area equals E of that material times delta BC, which is what I'm looking for, and my original length. Okay, so I have the internal force from B to C. I have my cross-sectional area. I need to go back and look at E. So as I'm looking at steel, my E value is 29,000 KSI, and my yield is 36 KSI. So before I can use this equation, what do I have to ask myself? Am I in the elastic region? Well, stress equals N over A equals force BC, 5,500 kips divided by 100 inches squared. And I can see that I have a stress of 55 KSI, which is definitely bigger than 36. So how do I have to calculate my strain? I have to go back to my stress strain curve here, and we are at 55. So if this is hopefully right in the middle, and now I'm going to take my straight edge and try to draw as straight lines as I can. Okay, there we go. We're coming straight across. And now I'm going to find this straight line right here, like so, and I'm just going to kind of drag it over until I meet, kind of like that. And we can come down. And I'm really close to just that 0.1, maybe 0.11, I'm going to call it 0.105 because I'm not quite on it. So I'm going to call that strain 0.105 inch per inch. And I know that strain is change in length from B to C divided by original length. Okay, I need to look. That's in feet. I need to find that in inches so that we can be consistent here. 144 inches. Okay, so the strain, I got off the stress strain curve, and the total length was 144 inches. So now I will go through and calculate these out, and I get 0.105, 0.105 times 0.105 times 144 equals, wow, I get a really big number here. I get 15.12 inches, and I guarantee you that's much, much, much bigger than the small strains that we get when we use stress equals E times strain. Try it out. I also know that it's going to be going downwards. Okay, it's going to be going downwards. Okay, so now let's do the same thing here. Let's look at A to B. And when I look at A to B, okay, it is aluminum. And we can go back to our equation sheet here. And aluminum, my E is 10,600 KSI. My yield stress is 60 KSI. So the first thing I have to check is stress equals. What does stress equal? It equals that internal normal divided by area. So I have 11,500 kips in compression divided by 20 times 20. So that's going to be 400 inches squared. Okay, and when I multiply this out, I'm going to find that I have not yielded, but I get 11,500 divided by 400 equals 28.75 KSI, which is definitely below 60. So I can just use stress equals E times strain. Okay, and that's N over A equals E times delta over L naught. So we're just going to use that delta equals, okay, we're going from A to B, delta equals NL over AE. Internal normal is 11,500 kips, and that's negative because we're in compression. Our original length is 15 feet, but we need to put that in inches. So it's 12 inches per foot divided by area, 400 inches squared. E, our modulus of elasticity, because we are in that elastic region of 10,600 KSI. And when I do this, I get negative 0.4882 inches. So if I want my total displacement of C with respect to A, it's going to be negative 15.12 inches plus negative 0.4882 inches. And so that total change is 15.12 plus 0.4882 equals, and I get a negative 15.61 inches. Or I could say it's going down or in compression, but I need to signify which direction it's actually going.